we're here to talk a little bit about security. Now, the question is, when can secure code become insecure code? And the first answer to this question is rather obvious. If you change the secure code, it may no longer hold the properties of secure code. It's been changed. But that's obvious. It's a duh. We're not going to talk about that today. The second case is much more interesting, however. If you have something outside of the secure code that changes, but the code itself does not change, there are circumstances where this alone can cause a problem. And this is what we are talking about today. Security is hard. Blockchain is hard. We know these things. Partially because blockchain technology just moves so fast. I am sure everyone in this room can attest to that. Any change, whether it's blockchain, in the real world, in your personal life, any change can cause issues sometimes. Now, one of the issues that we experience in the blockchain world is that when we consider the security of code, we often consider the scope of that code as only the smart contract code itself, isolated, in a black box, just floating in the air. But that's not how things work in the real world, because the code is deployed on chain, there are other things operating on the chain, and the chain is not constant. It's a living thing. Very few chains exist in isolation with no developers modifying it. So in effect, we have what could be called a butterfly effect. You can have a change somewhere on chain, on the chain, under the chain, over the chain, and this change can create changes elsewhere on the chain, perhaps unintentionally entirely. So the question is, are we building DeFi money Legos or DeFi quicksand? And that's what we'll talk about today. But first, a quick intro on how security audits work. If you were here last year, this slide may look familiar. Security audits, in brief, there is this security auditor who comes prancing in on a magic unicorn when called to do an audit, and after sprinkling just a handful of security dust on the smart contract code, leaves a massive stamp of approval saying this code is secure. Now, that's not quite how it works, but it's a close approximation by most estimates. But you will find these people on crypto Twitter. And on crypto Twitter, they will be saying audits are bulletproof, and I am the best auditor, and so. But really, this is nonsense, because in reality, audits are not bulletproof. Some of the problems with audits are that the audit scope is usually determined by the developers who wrote the code. And they will say, the context, the scope, it's just what I created. Just look at this. Don't look at anything else. I am the only one who matters here. That's nice, but we'll get to why that's sometimes not so nice. Anything outside of that scope is not really focused on. The developers really want people to pay attention to what they created for the security audit, but things outside of that that could cause problems are ignored. And there's this misperception of, well, if the bug is not in my code, then everyone's safe, life is good, the funds are safe, nothing to worry about. Not exactly. Now, I have a quick question for the audience, and I want you all to realize this is audience participation, so sit up straight, talking to you, and you. So sit up straight, take a deep breath, and raise your hand if you think forking secure code is always safe and secure. So I'm going to count just for the recording. We have 1, 2, 3, 4, 0. 0 hands raised. So either everyone in this room is a security genius, or you're all from Montenegro. But the question is why? Why is this not true? I mean, if we look here, compound v2 code and compound v2 code should be equal. They're the same. One is secure, why is the other not secure? This screenshot is from a GitHub repository that lists different forked protocols that have been hacked. This is just a small snippet from that repository, and this snippet is only focused on compound v2 forks. This is not to pick on compound v2, there are many other forks, but this protocol is one of the most forked. And unfortunately, you can see there's a long list of wannabe Compound v2 protocols that did not fare so well. The link to the repository with other hacked projects is at the bottom. Now, if I want you to take one message away today, it is the title of this talk and the title of this slide, that context is everything. When we talk about secure code, the context of the code matters. You cannot talk about the code in isolation. Consider the context. Now let's look at some of these context changes, why they matter, and what can go wrong. Some of the changes that add risk are governance design changes, governance decision changes. We'll get into the difference between those two. Blockchain parameter changes, which are actual changes to the blockchain, some upgrade. EVM chain differences. You cannot just deploy on every so-called EVM compatible chain. It's not exactly EVM compatible in all cases. And then there's just other protocol changes that we'll get to. But first, governance design changes. What is governance? What is governance design? Now, usually in a contract, there's an admin, at least when some protocols that are not fully decentralized are starting out, and this admin has special privileges. Now, in theory, this admin should be a multisig, but an EOA address is not the same as a multisig. This is pretty obvious, but you'd be surprised. Sometimes this can get missed. A multisig that is 1 of 1 is not the same as a 5 of 8 multisig. I think this is also obvious, but again, it's not actually in the smart contract code. All you see in the smart contract code is admin, and it's not deployed, so you don't know who the admin is. So basically, this entire slide is out of scope, so to speak. If the 8 multisig addresses of a 5 of 8 multisig are all owned by one person, like if you're owning all 8 addresses, it's not the same as if we've spread the addresses between 8 people in the audience here. And lastly, if you decide to use proxies, it's not the same as deploying without proxies. And I won't get into proxies because that's a whole nother story. I'd like to highlight this list of the top 10 vulnerability vectors as compiled by IFLX. The Block Threat newsletter is amazing, by the way. You should sign up. But if you think governance design is like totally out of scope, it doesn't matter. Things are safe. Don't worry about it. Number 4 on the list is stolen private keys. So clearly, governance is something we need to be thinking about. If it comes off the top 10 list, then I'll consider the opinion that this is a lower priority, but please, top 5. In Web 2, you may have seen some image along the lines of this. If you have a weak password, the website where you're trying to create an account will tell you this password is weak. Currently, we have nothing like this for multisigs. If someone wants to build this tool, I will happily recommend it, retweet on Twitter. We just need to build it. Governance decision changes. I love this meme. It's good. Okay, what do we mean by governance decisions? First example, and this is relevant for Compound v2 forks, is if a protocol decides, okay, we support 3 stable coins, let's add a 4th stable coin. When that additional support is being added, a governance proposal is usually created, and then people vote on it, it gets accepted, and it's implemented. But who's actually paying attention here in this process? This is key, because there are many things that can go wrong in this process. These 3 bullets are very common for Compound v2 fork hacks. The first one, if you support a token that has reentrancy, you can get hacked. If you support a token with insecure price data, you can get hacked. I'm sure all of you know about Oracle manipulation hacks. This is another big attack vector that unfortunately is still quite common. Lastly, if you support other weird ERC20 tokens that I haven't mentioned besides these 2, that's also often a problem. And if you think I'm using the term weird in a weird way, there's actually a repository for weird ERC20 tokens. Highly recommend it for anyone who wants to support many tokens because there are many edge cases out there. Second example of a bad governance decision. Lending protocols need governance to regularly update their market interest rates. During the bear market, there's less people actually using the protocol, so change the interest rates to adapt to the environment. Now, unfortunately, this doesn't always happen on the forks. Compound, Aave, they have big budgets, big treasuries. They'll spend money to get people to model what the proper interest rates should be. The forks don't exactly have that, and they might not be watching the main protocols, and honestly, this differs chain to chain. So if you're trying to adapt on one chain following what another chain is doing with their interest rates, it may not work out properly. So what can go wrong? If you set the interest rate models incorrectly, you can increase the risk of bad debt in the protocol, and potentially everyone loses from that. You can also modify the interest rates in a way that depositors are receiving less interest. Who does not like 4-digit APYs? I mean, come on. So you need to find a middle ground for this. This is a quick diagram of what I was just talking about. So let's take an example of DAI. Let's graph 3 different protocols choices for interest rates. Now, if you've used these protocols, you may be familiar with the shape of these lines. But basically, this is a piecewise defined interest rate curve. And if you look in the extreme case, when the utilization ratio is 90 and above, there can be very different results. So this is just one example of different protocols making different choices, and this affects the risk of depositing in the different protocols. So next time you see the 4-digit APYs, think twice. I could only find one good example of anyone actually giving advice on testing governance decisions before deploying them. So this is a very underexplored topic. So if you're interested in this, a lot of room for exploration. Third, blockchain parameter changes. And you might be asking me what I mean by this. The best example of this is Ethereum, switching from proof of work to proof of stake. Anyone who deployed their contract when Ethereum was proof of work had different assumptions of how things were working on the blockchain. This goes back to context is everything. When you're looking at the code, you're assuming, okay, certain things are true. But if the protocol layer, if the actual chain changes from proof of work to proof of stake, that's a shift in assumptions. And one example of a potential problem here that actually has real-world ramifications is Oracle manipulation. And this is specifically for a protocol like Uniswap. There is a time-weighted average price. And the way that this averaging works, it's over several blocks. In proof of work, the assumption was that you will not have one person building many blocks in a row. In proof of stake, I randomly opened up Etherscan on the day of making these slides, and I just scrolled through 2 pages, and I saw this one block builder had 5 blocks in a row. So I'm not even trying, and it's clear that this is a very different world than a proof of work world. So this impacted literally every contract on chain, and if there were certain assumptions made under the old circumstances, then you need to reconsider what's happening with the new blockchain change. So blockchains are not static, they do change over time. I'll give another very simple example in brief. There are always new EIPs coming about. You may have even attended a talk about a new EIP here. Sometimes there's a new opcode that's added. And sometimes if these opcodes are used, perhaps unintentionally, just when you compile your code, this may cause some difficulties, some problems. I won't get into this, but there is a blog post about possible reentrancy with this new opcode, and this is already deployed on Ethereum mainnet. This is just an example showing there's quite a few EIPs in case you didn't believe me. Now, when we talk about EIPs, these EIPs are usually deployed on Ethereum mainnet first. But they're not only deployed on Ethereum mainnet. In fact, these changes often get deployed to the other L2s, other EVM-compatible chains, often at a later date. And when I say they're deployed at a later date, that means that there are points in time when there are differences between these chains. And there is this great tool, EVM diff. They actually recently upgraded the tool, highly recommend it, but it allows you to actually compare different chains and see what the differences are. Because EVM compatible does not mean equal to mainnet. There are differences. This is just, pretty typical. Developers were fans of ETH mainnet, but no longer. There's developer incentives. It's all incentives. A quick example of what I was talking about with the EIP rollout. EIP 1559. It impacted gas fee pricing. It was deployed on Ethereum mainnet in 2021, but these other examples I gave, it could have taken 2 years to be deployed to other EVM compatible chains. So this means that the actual way that transactions are working and interacting with the code is different on different chains. So if you think you can write code and just deploy it on every EVM compatible chain and it's going to work exactly the same, you need to consider the ramifications. Not all chains are equal, is all I can say. Might be a little bit hard to see this, but this is actually a quick snapshot from Optimism docs, and this is actually showing even though they have the same EIP number implemented, they've changed some of the values in the EIP. So you have to go even deeper. The rabbit hole just never ends. So you might say, okay, they have this EIP, we're done here, it's good, let's ship it. But they've actually modified how the EIP is implemented. And again, if you have certain assumptions about how things work, it can be a problem. These are just some other EIPs with changes. I'm going to move quicker because I'm running low on time, I think. But I want to look at a very specific example. If you've used anything on chain, you've probably spent gas, unfortunately. I'm sorry. But this is a demonstration of how even something as simple as gas can have quite a big difference between the chains. In Etherscan and other similar tools like Etherscan for different chains, there's a way you can access charts, pre-created charts of different pieces of on-chain data. And this one is showing the average gas limit per block. So over here we have mainnet. It's about 30 million currently, but you can see it's changed. This is another thing that changes over time. So I was talking earlier about proof of work, proof of stake. That was a very big change. Everyone knew about it. But this is another example of there's a lot of stuff changing on chain. And then if you think it works the same on other chains, well, I think you already know the answer. I'm sorry. Over here we have a completely different number for BNB. And of course, it's really not fair to pick on BNB. I'm sorry. But we have to go to other chains as well. And over here we have Optimism and we have Linea. And look at this chart. This is a completely different shaped chart. It's not even close to the first slide. And then Linea, maybe because it started more recently, it's okay, they just chose one value, but they chose 61 million, whereas 30 million is on Optimism, and it's about 30 million on mainnet. So I don't even know how to describe these differences, but yeah, there's differences. And I didn't even include Arbitrum, because Arbitrum is off the charts compared to these, so we're not even going that far. So EVM chains, unfortunately, the differences are just going to keep propagating. It's just going to get worse from here. And as a demonstration, we have everyone's favorite XKCD comic. I believe at this point we are well beyond 15 competing EVM-compatible chains, but you get the idea. Other protocol changes. What do I mean by other protocol changes? When you deploy a contract on chain, most likely it is not operating entirely independent of anything on chain. At the end of the day, you're using an ERC20 token if you're in DeFi. If you're using some other application, there's probably some other contract you interact with that is not deployed by you alone. And what that means is you have these dependencies. Even if they're not imported into your smart contract, you're relying on other code that exists on the blockchain. And I will just give one recently notable example, which is the case of DeFi money Legos being used with Aave and Morpho. And this may have turned into one of the noteworthy examples of DeFi quicksand, not DeFi money Legos. So Morpho, for those who are not aware, it's basically built on top of Aave and Compound. We'll just talk about Aave. And building on top of other protocols is very popular in DeFi. It's one of the main narratives around how this space works. Now, unfortunately, there were sentences such as this one: Morpho optimizers are a leech on top of the Aave protocol. This does not exactly speak well of people building on top of other chains. And then this, of course, reached crypto Twitter, and there's talks about avoiding the drama in politics, but they didn't do a very good job avoiding those. What ended up happening is, I should go back a slide. What ended up happening is an entirely different mechanism for distributing rewards was implemented by Aave. So if you were building on top of Aave like Morpho, the protocol you built on top of just changed. And now you have to rethink what you're even doing with your design. So this is just one example of like the narrative around DeFi money Legos really has a lot of dependencies built in, and code that supposedly is on-chain and cannot be changed, well, sometimes there's changes. And I'm going to give one other example of a change that really had a massive impact when it came out, and even now there's impact, and that is flash loans. So flash loans have not always existed. At one point, a protocol created this idea of flash loans where you can borrow money within the same block and pay it back. And sometimes this is even free. You can borrow millions of dollars instantly and then repay it in the same block, and it's free. It's amazing. You can be a millionaire for like a nanosecond. But unfortunately, this allowed anyone access to becoming a millionaire. And when you have large amounts of capital, you can reach edge cases in protocols that are not normally expected. This is a small sampling of headlines. It only took me maybe 3 minutes to collect these all, but these are hacks from flash loan attacks. It's a very common attack vector because no one's thinking about $100 million rushing into their prototype protocol and then rushing back out. And a lot of things can happen, things can break. So this is an example of something when code was deployed, you may not have had flash loans. You might have seen that there was only one person who was a whale with a large amount of tokens and said, you know what? They're safe. I'm not going to worry about them. We're good. And then flash loans comes out. It's on a distant part of the chain, but it can have ramifications across everything on chain. So this is just another example of even if you don't change secure contract code, the chain can change you. Some other quick examples of protocol changes that can happen elsewhere on chain and impact your protocol or a protocol you're deposited into. When there are new types of hacks discovered, this is like a possible chain reaction can occur. So if there was code that has always been insecure, but it was only just realized to have a vulnerability, suddenly many different protocols with the same vulnerability can get hacked. This is an example of knowledge changing in the ecosystem, the second point. And yeah, this has happened in Compound forks, yet again. I know I'm picking on Compound, but there are so many Compound forks, it's just too easy to do. There have been many Compound forks hacked due to the empty markets bug, which I won't go into, but it's listed on that GitHub that I mentioned earlier with all the hacked fork protocols. There's lots of risks. What do we do? Can we prevent all of these before the protocol is deployed? And my answer is no, because before the code is deployed, you don't have the full context. Code working on-chain is very different than code in isolation where you don't even know what parameters are put into the constructor by the person deploying the contract. So should we give up? I mean, this is a hard problem, but no, I say no. You don't have to give up. So what is the answer? And the answer is context is everything. Security extends beyond an audit, and you have to consider the full context of what you're dealing with. You cannot just deploy code and assume the chain is going to remain as is. The chain changes. So a few quick suggestions, because of course now I've made everyone in the audience panic, and you're wondering what to do about it. So a few suggestions before you deploy your code. You can include the deployment script in the security audit scope. You can make plans around which chains are going to get deployed on. You can create governance decision review processes. And then after launch, I have some other suggestions, but I'm running out of time, so we won't go there. So, brief summary. Learnings. This is where bugs are usually expected, the contract code. But realistically, the bugs can exist outside of that. Context is everything. So these are the points we've covered today. And that is everything. Just remember, context is everything. I think I'm out of time, but I'm not sure.
Hi. So this reminds me to a common security presentation that is usually explained when doing embedding programming. So we have many problems that we usually expect from hardware changes, from some standards, or from these kind of stuff. And usually they are tackled by, standards itself, and of course trying to do some different programming paradigms, such as functional programming, where it's written in certain ways to explicitly state when something is unsecured. So just for audience to be more precise, if I try to grab something from disk and somebody removes the disk or change the data or change the file on the disk, the output of the function will be different. So these are the common things that are done. Some smart contracts are therefore written in some languages that are more that are known to better tackle these problems. So can you elaborate on this, whether you will suggest any particular chain or language that is more suitable to track these problems in other than Solidity or something? And of course, to go back to the first slide where you put the link to these slides. Thank you.
Good point. Let's get that QR code. And of course, the QR code slide is a test, because anyone who actually takes out the camera and uses a QR code, I'm sorry, honeypot. So I would say that for your example of embedded programming and the security around embedded hardware, I would actually use the analogy of Web 2, like the internet. If you deploy a website, you may be using packages that are secure today, but insecure tomorrow. This is one example of the fifth point where the ecosystem knowledge changes. You may also be running the website in the year 2005, and then in the year 2015, there's HTTPS. And you didn't have that option early on, but now the actual internet has changed how it's operating, so you should upgrade. So I don't think there is a really good answer for a chain that is solving these issues. This is just something you have to deal with when there's a network, there's software that needs updating, and everything is very interconnected. I'm sure you've been to a website where there's a broken link, and this is just a simple example of the equivalent of money Legos in Web 2. So it's a very difficult problem to solve, but I suggest not giving up. Their context is everything. Thank you.